Okay, we're going to start with a simple situation where we have one flight from Philadelphia to Albany, and the seat capacity is 100. Okay. Now we have two fare classes. The business class or Y class is $300, and the demand for that follows on average 330 with a standard deviation of 10. And a Q class, which is economy class fare, is $100, and the demand follows 90 for mean and standard deviation of 40. So basic assumption is Q class passengers make their reservations before the Y class passengers. So we have to now say, okay, how many seats are we going to set aside? Because if we don't set aside, so then all of the seats, presumably, because if the demand mean is 90, then quite a few times it's going to exceed the capacity, so all of the seats will get sold off, and we'll have nothing left for the higher price fare. So the competing situation here is that you set aside too many seats, and then we are not able to sell them at the higher price, so we have empty seats that we could have sold at $100 price. You set too few, so then we have sold those seats that we could have sold at $300 at the lower price of $100. So this is the situation, and we're going to look at three strategies, and we will expand on these three strategies as we go along, discussing new concepts and new techniques in the chapter. So we're going to start off with strategy number one, no control. So that means we just don't set aside any seats at all, let the chips fall where they may. So we'll be able to sell Y class seats only if there are anything left over which were not sold to Q class. Okay. Strategy two is we'll set aside the mean number of seats. So like here we are expected the mean demand for Y class to be 30. So that's what we're going to set aside. We're going to set aside 30, and we will only sell up to 70 seats for Q class. So we'll call that mean control. And then the Littlewood controls, and we're going to make an assumption here. Okay, we're going to make an assumption that this transition point, that is the expected revenue from a possible future sales at $300 a seat, okay, as against $100 of definite sales, that falls at 37, okay, which comes from a paper written with this analysis, and it turns out that it is really not 37, as we will see later in our simulations, but we will just go with the suggested number of seats to hold back, which is 37. So these are the three strategies we're going to set up in at risk. And here we have to also think about one thing, and which is when we simulate, we can't have demand on the negative side. So if you look at standard deviation being 40, okay, so more than 2 standard deviation plus a little bit, so if you get an x value that is like 3 standard deviations away, which is not at all very unlikely, it's quite possible, then you end up with negative demand. And obviously that's not possible. So we have to set up our normal, we are assuming normal distribution, right? So we have to set up the normal distribution in such a way that it gets truncated at 0. So we don't get any negative values for demand. And we have to do that. And here is a screenshot of how it is done, how to truncate. So we need to click these 3 buttons and then select. Right now it is no truncation, and we need to select truncation. No truncation means nothing is truncated on the left side or on the right side, and truncation can be done at different ways. So we can have a shift factor. So you can you can shift the mean up or down and then do the truncation, or you can do the truncation and then shift up or down. So that's why you have all of these different possibilities. Value truncation applied before shift, value truncation applied after shift, and then you have percentile truncation, no truncation, and then the shift factor. But we're going to look at no shift factor. So it really doesn't matter whether we choose before shift or after shift, because we're not going to do any shifting. So we just select one of these two and then set that truncation value. We will see how to do that in just a second. And as I mentioned just a minute ago, it turns out that 37 is not the place where the transition occurs when expected value of the revenue for future sales exceeds the definite sale of $100. And again, I talked about this, since Y-FAIR is 3 times as likely, even an analytical equation method, you can see that if you take it turns out that, if you look at the normal distribution inverse curve, it turns out that it's 34 at which you have a transition from the future expected revenue exceeds the $100 definite revenue, and it goes like this. So then the number of seats set aside for X such that mu is 30 and sigma is 10, which is for the Y class. Okay, so then you need a normal curve such that the top tail, the upper tail, has a probability of 1/3. So if the probability that the demand will exceed that particular level is 1/3, then you get 1/3 times one more seat, that you're selling one more seat, okay, will be greater than 1/3, okay, from that level. So the cumulative probability will be 2/3 at that point of transition. So if you go norm INV 2/3, and then the mean is 10 and the standard deviation is 30, okay, so if you do that, okay, so norm dot INV, right? So probability is 2/3, mean is 30, and standard deviation is 10, then you get 34.3. So 34.3 is the point, and let's round it to 34. So we reserve 34 for Y class, right? The rest of it you sell, and that would be the point at which this Littlewood pricing will kick in. But let's set up the simulation model, run the simulation model, and of course the strategy 3 is going to be 37, and then we will do further analysis for 30, what happens. We'll put up a curve and then see where the maximum revenue occurs, and you'll see that it is not at 37, it's really at 34.